And we want to establish callouts. Sticky Macs, like I mentioned, typically are that's a pretty fatal problem to have if you drop one of these devices in remotely, because it's a real sign that something's going on that shouldn't be going on. So try to avoid that at all costs. However, you can typically force an 802.1x re-authentication without any sort of ill effects, simply because there's going to be so many different devices out there that reboot periodically, or the connection goes away, or a switch gets rebooted or something. So seeing re-authentication traffic usually doesn't set off any alarms. Now, port security, a single stray MAC address flying across the wire will be the end of you. So you have to make sure that no traffic leaves until everything is set up. And we're going to start dark and slowly bring up functionality until we're good to go. So things that have bitten me in the past. Excess services. Apache is really good at that. What's the first thing Apache does when it starts up? Sends out a name server request for its IP address, because typically it's going to be host www.cnn.com. What's the first thing it does? Oh, who is www.cnn.com? Sends out a name server request. Well, a name server request goes on the wire, so if you're not paying attention, that's something that can happen in the background. Many other services also do the same sort of thing. IPv6. Most modern kernels will automatically have IPv6 support enabled, and there may or may not be IPv6 traffic on the wire that you're on. But since I'm not doing anything with IPv6, it's best to disable it, because it has burned me in the past. DNS, like I mentioned, sometimes simply starting networking under Linux can cause a DNS query to go out. So I typically blank out the resolve conf to make sure that doesn't happen. And then ARP is usually the culprit for all of the woes when it comes to tripping port security. Because everything you do, if it doesn't know how to get to that particular IP address, it fires off an ARP request. So simplest thing to do is to make sure you don't fire off any ARP requests. ARP tables is a tool that allows you to block all ARP traffic from an interface. Now, using the output chain here, the output chain is only used by traffic that leaves the local network or leaves the local device. So traffic going across the bridge actually traverses the forward chain and not the output chain. This is a quick overview of the basic chains that IP tables, ARP tables, and EB tables. Pre-routing, all traffic coming into the device passes through the pre-routing chain. Forward is traffic moving from one interface to another, so the bridge traffic traverses the forward chain. Input is traffic destined for the local device. Output is traffic leaving the local device, and post-routing is all traffic that leaves the device, or including the forward. So all traffic crossing the bridge will go pre-routing, forward, post-routing, so we can manipulate the output chain as much as we want and not affect any of the traffic that's going on with the client. So MAC addresses are actually pretty easy to spoof, but since we're operating at layer 2, they can cause some unusual problems. And since we need to interact at layer 3, in order to be able to remotely communicate with the device, there's a better solution out there, and it's called EB tables. EB tables basically allows you to specify a series of rules that operate on the bridge itself. And the best thing it does is allows you to NAT with MAC addresses. So yeah, we want to be able to interact with the device. Makes sense. We can use source NAT with IP tables to to NAT all of our traffic to make it look like the device that we're in front of. Now, with source NATing, there is a quick caveat, namely that in the most modern TCP/IP stacks, connections are tracked internally by source IP, the tuple, source IP, source port, destination IP, destination port. Since we're stealing a client's connection, if we interact with the same device that our client that we're stealing is interacting with, we're automatically matching potentially 3 out of 4 of the connections. So if we're going after the local domain controller on port 135, we're matching the source IP, the destination IP, and the destination port. So the source port is the only source of randomness that we have left to play with. So what would happen if we actually jumped all over a connection? In all honesty, the connection would probably reset and things would move on to normal, but it would be weird to stomp all over an active client's connection, and it's not terribly stealthy. And in the theoretical world, we have basically a 1 in 64,000 chance of stomping on a connection that way. However, Microsoft, in their infallible wisdom, thought that 64,000 ports was just too big of a number. So on 2000 and 2003 and XP, TCP and UDP source ports would pretty much always be in the range of 1025 to 5000. That is less than 64,000. You actually have, on an active machine, a really good chance of stomping all over that. Plus, if your traffic, when you NAT out, uses port 6000, that's weird, because all XP and 2003 traffic will be from 1025 to 5000. And then Vista 7 2008 uses 49.152 to 65535. So what we can do is we can specify ports that we use with our source NATing so that we will restrict our traffic to be in a particular range. Now, in this particular example, I'm restricting it to 1,000 ports and assuming we're going after a Vista 7 2008 client. And it's in the high end, so the average, unless you're on a machine that has seen a lot of activity, you'll occasionally run into a chance of stomping all over it, but hopefully you won't. We can use destination NAT to create a virtual service that only we can connect to. So by SSHing to, say, port 9876, we can have the IP tables pick off that connection and redirect it to localhost 22, and we can SSH into the device that we're using. So we can use this as a call to the machine. So you SSH to the client, and the client computer will never see it. It will get picked off by the bridge. And we can further restrict that by putting a source IP address on the statement there, so that only traffic coming from one particular IP or a series of networks or whatever you want. So if anyone else tries to go to that port, it'll just go right to the computer and won't see anything. We can also set up a reverse shell where we have the bridge call us. And in all honesty, this is probably the safest way to go, because if you're in a network that has 802.1x, you're probably going to not allow random traffic from the outside world directly to your workstations. So it would be best to call out, but I've implemented everything both ways to just demonstrate the technique. And there's plenty of ways to phone home: SSH, OpenVPN, Netcat, whatever. It's all good. So we need a layer 3 IP address in order to do any of the translations with the bridge. I chose something in the 169-254 reserved IANA range because this is the range that you will self-assign if you don't have access to a DHCP server. So in other words, it's something you should never see flying across the wire. You're not going to be screwing with their IP space. You shouldn't have any problems interacting on the wire. Yeah, before we get too far gone, I want to mention that I haven't found a good way using this device to actually interact directly with the client behind the bridge. You run into little problems like, since I'm stealing his network connection and I'm behaving like his IP address, what source IP address do I use for any communication with him? I mean, I could set up a remote one and then just filter out all the traffic, but you need to make sure it's something that he wouldn't want to visit on a normal basis. It's really kind of a pain in the ass. So I haven't found a good solution to it. So the current scenario, we've got since our group does full scope pen testing, we've got folks walking around inside their building, pretending to be employees, doing all sorts of fun stuff. So they managed to give us a printer config. So we're going to take the information on the printer config, because if you've looked at any network printer configs, they've got MAC addresses, IP addresses, network information, all that stuff, and pre-populate one of our little devices so that we can imitate the printer and then interact with that device. So once again, set up some shell variables, set up the MAC addresses, set up the IP addresses, the network range, the interfaces that the bridge is using, bring up the bridge, start IP tables and ARP tables in drop mode so that no traffic will leave the device while we're configuring it. One of the interesting side effects of creating a bridge in Linux is what MAC address gets assigned to the bridge. It's actually either the highest or the lowest MAC address. I can't remember which one it is, but invariably it's going to be the one you don't think it is. So I have a line in here using MAC changer to force the bridge IP to always be the switch side interface. That way, moving forward, we always know what to use in our rules. So we bring up the bridge interface, we add the local network via the bridge, we set up the default gateway, and we use the post-routing EB tables rule with NAT to NAT the MAC address of the bridge to the MAC address of the computer. So now all Ethernet traffic, all Ethernet frames look like they came from the computer behind us. There's the IP tables rule to set up the destination NAT. There's the source NATing rules that for TCP, UDP, and ICMP start up an SSH server, which is listening, I believe, on the bridge itself. And then we drop the ARP tables and the IP tables rules. And now we can interact with what's going on the wire. So now, I think I've got everything set up. So what I've got going on here is I have a plug that's in line with